This Californian earthquake has become the international benchmark for earthquake testing and engineering and is recognised by the New Zealand Earthquake Standard. Test 1 and 3 subjected the test house to 0.89 times El Centro. This represents a strong earthquake of approximately 6.2 on the Richter scale. No sign of any damage from these tests were observed. This level of loading is greater than ultimate limit state levels for Auckland and Hamilton, and is approximately equal to the ultimate limit state level for Dunedin. It also represents the serviceability limit state for high earthquake regions in New Zealand. In Test 2, the walls without openings were subjected to ultimate limit state out-of-plane loading. After this test, only small hairline cracks were observed in the plasterboard lining at window top corners and some very limited hairline cracks at locations in the brick veneer adjacent to the window opening.
Well, the ties and the insulation suffered no effects at all. The stud seemed to move about 2 millimetres or so. Brick veneer just moved as a solid unit, no sign of any local deformation or cracking, and no sign of any damage whatsoever.
In Test 4, the excitation was applied to subject the walls without openings to maximum considered earthquake, MCE, loading in the out-of-plane direction. This MCE loading was equivalent to 1.72 times El Centro, which represents an earthquake of 8.4 on the Richter scale. MCE is defined as the maximum considered earthquake representing a very rare event with a return period of 2,500 years, compared to the ultimate state limit earthquake that has a return period of 500 years. This level of loading required to be met for the steel framing and brick tie system to satisfy code requirements in New Zealand. After this test, a minor increase in cracking to the plasterboard at window corners was observed. However, there was no visible damage to any of the ties. Test 5 consisted of subjecting the test house to an MCE level of load in the other direction, which resulted in the walls with the door and the window being subject to out-of-plane loading. The test house passed all the requirements for MCE and everyone involved was delighted with the excellent performance. The decision was then made to increase the loading to determine how much reserve strength remained in the test house. In Test 6, the load direction was changed again to load the walls without openings in the out-of-plane direction. In this test, the loading was 1.16 times MCE level, which was equivalent to 2 times El Centro. As can be seen, there was no noticeable rocking of the brick piers at the base of the window. After this test, hairline cracks that extended across the pier base were observed. However, there was no visible damage to any of the ties or the steel frame. In Test 7, the level of loading was increased to 1.34 times the MCE level, which was equivalent to 2.3 times El Centro. As can be seen, there was an increased rocking and cracking of the brick piers at the base of the window during the test. From a visual inspection of the test house, there was no evidence of pull-out of any of the ties or damage to the steel frame. In Test 8, the level of loading was increased further to 1.51 times the MCE level, which is equivalent to 2.6 times El Centro and equivalent to a magnitude 9 on the Richter scale. As can be seen, there was further increase in rocking and cracking, which was augmented by partial failure of the connection between the diagonal brace and the top plate to the walls with the openings. Again, there was no sign of tie pull-out from the steel frame or the brick veneer. However, there was evidence of the ties causing a permanent indentation in the thermal brakes. In Test 9, one last attempt was made to fail the test house by increasing the loadings to 1.57 times the MCE level, which was equivalent to 2.7 times El Centro and met the capacity of the shaking table at the University of Melbourne. This was equivalent of a devastating earthquake exceeding 9 on the Richter scale.